Thank you very much for the nice introduction, Dr. Sosa, and thank you all for having me here today. It's really an honor for me to be here to talk to you about some of the research that I've been conducting in the U.S. As Dr. Sosa said, I'm going to talk to you today about improving total nitrogen deposition budgets in the United States and some research that we need to conduct to improve deposition budgets for critical loads assessments and for ecosystem health studies. And when I refer to budgets, I'm referring to determining the total amount of nitrogen that deposits to ecosystems and determining the relative contributions of the different nitrogen compounds to the total budget. I want to acknowledge the co-lead for this work, Dr. Gregory Beachley. He's also with the U.S. Environmental Protection Agency. But a large number of collaborators worked on this synthesis that I'm going to present to you today, and I want to acknowledge them at the end of the talk. So an outline for my discussion today, I want to talk to you a little bit about the U.S. National Atmospheric Deposition Program and the committee that pulled together the synthesis that I'm going to present to you today. A little bit of background about reactive nitrogen, though I think all of you know something about reactive nitrogen in the atmosphere. I want to talk about some of the air regulations that are relevant to reactive nitrogen that motivate the research that I'm going to talk to you about. And then critical loads for assessing ecosystem health. I want to talk a little bit about some of the methods that we use for developing total deposition budgets. Then I want to spend some time discussing the current patterns and trends in deposition to set the stage to then talk to you about the key knowledge and data gaps that we need to address to improve deposition budgets. And then finally, I want to leave you with some examples of broad, overarching research needs that cover a number of different topics, but where more collaboration is needed to advance deposition science. So a little bit about the National Atmospheric Deposition Program. The NADP, as we refer to it in the United States, is a program that operates a number of different monitoring networks, and we use the data from these networks to develop the deposition budgets. The most important network is the National Trends Network. This is a precipitation chemistry network, more than 250 sites across the US where we measure the chemistry and the amount of deposition on a weekly basis. There's also a smaller precipitation network where we measure daily precipitation and deposition. NADP also operates a national monitoring network for ammonia, the only ammonia monitoring network in the United States. So the NADP manages all of these programs, and there's a central analytical laboratory and a program office, but the NADP is interesting because it's really guided by committees. There are committees for technical aspects of the network operation, administrative details, but there are also science committees that guide the direction of the program. And the committee that developed the synthesis that I'm going to present today is the Total Deposition Science Committee. So the mission of this committee is to improve estimates of atmospheric deposition by advancing the science, provide a forum for exchanging information among atmospheric scientists, ecosystem scientists, resource managers, policymakers. And this committee is interesting because it includes participants from federal agencies, academia, state government, private industry. This committee and our collaborators developed a white paper on the state of the science and the research needs for nitrogen deposition to prioritize the committee activities over the next several years. And this white paper is what I'm going to talk to you about today. We developed the white paper over a period of probably 2 years. 3 years ago, we started working on this. And the white paper is in total available at the NADP website. And we also developed a couple of special issues at EM Magazine and Science of the Total Environment for different pieces of the white paper to be published in the scientific literature. So if you're interested, I can make sure that you have access to this information. So that's a little bit about the National Atmospheric Deposition Program. Now I'll talk a little bit about atmospheric reactive nitrogen and nitrogen deposition. So this is what all of the forests look like in the United States. Perfectly spaced trees, they're all oak trees. I'm just kidding. But the idea here is that nitrogen can deposit to the Earth's surface through wet deposition processes and dry deposition processes. And this is really the area of research where I spend most of my time, determining dry deposition rates using micrometeorological techniques to directly measure air surface exchange. So dry deposition includes turbulent, diffusive, and chemical transfer of gases and particles to the surface. So if we take both dry deposition and wet deposition together, that's the total nitrogen deposition. So in terms of discussing the atmospheric nitrogen pool, there's so many different reactive nitrogen compounds in the atmosphere. It's helpful, for me at least, to group them into some different classes of compounds. So here we have one group is the inorganic oxidized nitrogen that we're all familiar with. Nitric oxide, NO2, nitric acid, nitrate aerosol. The oxidized nitrogen compounds are primarily emitted from fossil fuel combustion, mobile sources, energy generation. So that's a large group of compounds that we know relatively well. And this is the group of compounds that are regulated in the United States. Then there's the other inorganic pool of nitrogen, the reduced nitrogen forms. This includes ammonia and its reaction product in the atmosphere, ammonium aerosol. And these compounds are very different because they're largely emitted from agricultural sources. In the United States, confined animal feeding operations, ammonia emissions from animal manure, and fertilizer account for about 80% of all the emissions. But we're learning that mobile emissions are also a source of nitrogen, of ammonia. But in the US, mostly agriculture is the source of ammonia. And once this ammonia gets into the atmosphere, it reacts with acidic gases to form ammonium nitrate, ammonium sulfate aerosol. So this is a group of compounds that I'm going to spend quite a bit of time talking about. Then here is the third group of compounds is organic nitrogen. And this is the group that we have the least information on, and it's the most chemically diverse, I would say. So these are natural compounds and biological material that is emitted from forest fires, oceans, dust. There are also secondary reaction products in the atmosphere that contain organic nitrogen. These are organic nitrates and things like that in the atmosphere. So this is a large group of very chemically diverse compounds that we don't know as much about, but that is very important in terms of the reactive nitrogen pool. So what are the air regulations in the US that are relevant to reactive nitrogen deposition? So these are the regulations that motivate this research on reactive nitrogen deposition. And there are a few different regulations that I'll go over very briefly. The biggest ones are the National Ambient Air Quality Standards. So these are the standards for several criteria pollutants in the United States. And we have the primary NACs. These protect human health. And the reactive nitrogen compounds of interest there are nitrogen dioxide and PM2.5. We regulate the PM2.5 mass, but as we know, PM2.5 contains nitrate and ammonium. It contains some reactive nitrogen, and so the NACs for PM2.5 is relevant to reactive nitrogen. But the standard that protects ecosystem health is the secondary standard, and it protects public welfare, which includes ecosystem health. NO2 is the compound that's regulated that's most directly relevant to the secondary standards. But an important detail here is that these standards are concentration based. They're not based on actual deposition to the ecosystem. They're based on the air concentration and the exposure to the air concentration. So while the standard really only directly addresses NO2, we know that the ecosystem is responding to the total exposure to nitrogen. So it's not just NO2. The ecosystem is responding to all of the different forms of nitrogen. So when we review the standard on a periodic basis to see that it's protective enough, we consider all the forms of nitrogen in terms of the ecosystem impact, and then we look at those forms of nitrogen that are subject to regulatory control. So the secondary standard for reactive nitrogen is a big driver of this research in the US. But there are some other regulations that are relevant to reactive nitrogen. As I mentioned earlier, reactive nitrogen contributes to particulate matter formation, and this particulate matter affects visibility and haze in our natural areas. And so the regional haze rule calls for state and federal agencies to work together to improve visibility in our wilderness areas like the Grand Canyon. So these are referred to as our Class 1 wilderness areas. So the rules to control visibility and keep and improve visibility in these areas are also relevant to reactive nitrogen. So these are the regulations that are relevant to air concentrations. So we also have a regulatory framework that we use that's directly related to deposition. So you may have heard of this concept of critical loads. Critical loads are used by the EPA and the other federal agencies like the National Park Service, the National Forest Service, to protect ecosystems from too much nitrogen deposition. So this is another framework that we use to address nitrogen deposition. And the critical load, this is the technical definition. It's a quantitative estimate of an exposure to one or more pollutants below which significant harmful effects do not occur. So this is the amount of nitrogen that the ecosystem can tolerate before you begin to see negative impacts like eutrophication of lakes, rivers, and coastal zones when they receive too much nitrogen. In terrestrial systems, too much nitrogen can lead to reduced diversity of vegetation species. And in forests, too much nitrogen can lead to forest soil acidification and reduced resilience to things like climate variability, pests, frost, things like that. So the critical load is the amount of nitrogen deposition that the ecosystem can tolerate. But to know if we're exceeding the critical load, we have to know the total amount of nitrogen that's depositing. So to evaluate the critical load exceedances, we need an accurate estimate of total nitrogen deposition. So moving on, that's the backdrop for what motivates this research. Well, now what are some of the methods that we use for developing these total nitrogen deposition estimates and for determining which compounds are contributing the most to the total? Well, we can directly measure wet and dry deposition. I talked to you about the National Trends Network. So we're directly measuring wet deposition at more than 250 sites around the US. We can also directly measure dry deposition using a number of different micrometeorological techniques. But as we're going to talk about a lot more, those techniques are expensive, they're complex, and so we really don't have very many measurements of dry deposition. But if we did, we could develop these total deposition budgets entirely from measurements. That's rare. What you more commonly see is the use of site-specific inferential models for the dry deposition component. So we measure the air concentrations of the species that we're interested in, the micrometeorology, the surface characteristics, and we model the dry deposition for a specific site. So that's kind of the second best thing. We can also use output from regional chemical transport models. These are the big gridded transport models that simulate emissions, atmospheric chemistry, transport, and deposition. And so you'll see that we use a lot of output from chemical transport models for deposition assessments over the national scale. And then this is a technique that we're using more frequently in the United States, is combining measurements and output from chemical transport models. And this is called measurement model fusion. And the technique that I'm going to use today to describe some of the total nitrogen deposition budgets and some other details is the TDEP MMF procedure. So this is a measurement model fusion approach developed by Donna Schweedy and Gary Lear, and they're part of this TDEP science committee that I described to you earlier. So development of this technique was one of the first real successes of our science committee, and now we're using it regularly for deposition assessments. So I am not going to go through this entire schematic, but I will tell you sort of the basic details of the measurement model fusion. We use the wet deposition measurements that I mentioned. We use them and we spatially interpolate them, and that's the wet deposition component. So we're using measurements for that. Where we are measuring air concentrations in our routine monitoring networks like The Clean Air Status and Trends Network measures ammonium aerosol, nitrate aerosol, nitric acid at 100 sites around the country. We use the measured air concentrations and we apply deposition velocities from the chemical transport model to estimate the dry deposition component for those species where we measure their concentration. So that's where the measurement model fusion comes into play. And then for those compounds that are not measured at our routine monitoring sites, we use the output from the CTM directly. And we'll talk a little bit more about that later. But the idea is that by fusing the measurements and the model, we get a more accurate deposition estimate than we could derive from the model by itself. Okay, so now with that as the backdrop, let's talk about some results, some of the current trends and patterns in nitrogen deposition. So again, I'm going to present results using the TDEP measurement model fusion procedure. First, we're going to look at annual total deposition averaged over the year 2014 to 2016. And this is total nitrogen deposition from both wet and dry deposition, all of the compounds that we either measure or model. And the red colors indicate those locations with higher deposition rates. So a little bit of basic information. Across the continental US, the total deposition ranges from below 1 kilogram of nitrogen per hectare per year, which is very low, to more than 70 kilograms of nitrogen per hectare per year. And the average, if you look across the US, is about 6.5 kilograms of nitrogen per hectare. So to put that into perspective, the critical loads that we talked about earlier can range from 1 kilogram of nitrogen per hectare for very sensitive species up to more than 10 or 15 kilograms of nitrogen per hectare. So you can see how the range of measured deposition compares to some of the ranges of typical critical loads. The lowest deposition rates occur here in the remote southwest and western part of the US, and the highest deposition rates appear in the Midwestern US and in southeastern North Carolina. This is where I'm from, in North Carolina. And we grow a lot of pigs, turkeys, chickens. So we have a lot of agriculture on the coastal plain of North Carolina. And what you can see is that these highest deposition rates tend to occur in agricultural areas where there are emissions of ammonia from agricultural processes. So that's a theme that you're going to see throughout this talk, is that there's a close connection in the United States between agriculture and nitrogen deposition. So that's kind of the big picture. How do deposition rates look spatially across the United States? But now let's start looking at the different pathways of deposition and the different species that contribute to deposition. So one really interesting pattern that has some implications for the accuracy and the uncertainty of the total deposition is, what does the dry deposition fraction contribute to the total? So this is what I'm showing you here. This is the percentage of total deposition that's contributed by dry deposition alone, again averaged from 2014 to 2016. And so these red colors indicate areas where dry deposition is dominating the deposition budget. Is very important. And if you look across the US in total, dry deposition on average contributes slightly more than wet deposition. So it's the primary pathway of deposition on average if you look across the US. But if you look at some of the areas of the Southwest and on the eastern side of some of the mountain ranges, you can see that dry deposition really dominates the deposition budget, contributing 90% or more of total deposition in a lot of areas. In the eastern US, we see, again, large contributions from dry deposition occurring in agricultural areas, where we see dry deposition of ammonia. So again, my home, eastern North Carolina. But we also see from the models an indication that urban areas are areas where there are high deposition rates of NO2 associated with mobile emissions. So you can see some of the larger cities in the southeast, Atlanta, Charlotte, North Carolina, and then up here into Washington, D.C. and New York City. These urban areas seem to be hotspots for dry deposition of NO2. So that's another interesting feature that we're going to talk more about. But the idea here is that dry deposition is modeled. Even in using the measurement model fusion technique, we're still using the model for part of the deposition process. So it's therefore more uncertain than wet deposition, and so this reliance on models to determine the primary pathway of deposition is an issue that we're going to talk more about. So moving on, that's kind of the big picture of is wet or dry deposition contributing more, but what about breaking the total deposition budget down into different species? What I'm showing you here is the percentage of the total that's contributed by NHX compounds. And NHX includes ammonia and ammonium aerosol, both wet and dry deposition. So this is just looking at the contribution of the reduced nitrogen forms to the total deposition number. And again, these red areas indicate those places where these compounds are contributing the majority of the budget. So if you look across the US, these NHX compounds contribute more than half of the budget over large areas. And again, we see the largest contributions in the Midwestern US and Eastern North Carolina, consistent with patterns of agricultural emissions. So the key point here is that emissions of ammonia are not currently regulated in the US. As I said earlier, we regulate emissions of oxides of nitrogen, but we don't regulate ammonia. And so if you're in an area and you want to protect a forest in Colorado or some area where most of the deposition is being contributed by these reduced forms of nitrogen, you don't have much in the way of regulatory control to reduce nitrogen deposition. So this is creating a problem in some areas for achieving critical loads. So in the last map, you could see reduced forms of nitrogen are very important if you look across the US. But their relative importance has increased over time. They did not always contribute that much to the total deposition budget. So since 2000, the contribution of reduced nitrogen to the total budget has dramatically increased over time. So what I'm showing you here are some other maps that break the budget down into oxidized nitrogen. So this is NOx, nitric acid, the oxidized inorganic forms of nitrogen, and their total deposition in 2000 to 2002, and then 2014 to 2016. And what you can see is a dramatic reduction in total deposition of oxidized nitrogen. And this is directly related to a 50% reduction in NOx emissions under the Clean Air Act, the NAAQS that I spoke about earlier. So because nitrate deposition is going down, the importance of reduced forms of nitrogen is going up dramatically. So most of this change is due to NOx emission reductions. But if you look at the reduced forms of nitrogen in early 2000 versus 2014 and 2016, you can also see more deposition in the Midwest. So our ground-based and satellite observations are also showing increases in ammonium wet deposition and in ammonia air concentrations in some areas of the US during this period. So oxidized nitrogen deposition is coming down, concentrations and deposition of reduced nitrogen are going up slightly, and so the relative importance of reduced nitrogen is increasing over time dramatically. So that really has some implications for our monitoring networks, which we'll talk about momentarily. So that's the backdrop in terms of the patterns of deposition, wet versus dry pathways, and the contributions of reduced versus oxidized forms of nitrogen to the budget. And so that sets the stage for us now to talk about some of the knowledge and data gaps that need to be addressed to improve our deposition budgets. So this is really the details of the white paper that we developed that I'll talk to you about now. And so some of the issues that I'll talk about are the completeness of the deposition budget. Are we including all of the important forms of nitrogen? Spatial variability of ammonia in agricultural areas. Are our monitoring networks sufficient to resolve that spatial variability? Do we know dry deposition well enough, and what do we need to do to improve our understanding of the spatial and temporal patterns of dry deposition? We noted that deposition in urban environments is important. Are we monitoring those environments sufficiently? We know that we need to improve dry deposition models because we rely on them so heavily for our deposition budgets. And then the last point I want to talk about is some of the uncertainty that comes along with taking an output from a gridded CTM and downscaling it to a specific location for assessing critical loads. So these are just some examples. This is not a full list of what we cover in the white paper, and nor are these ordered in terms of importance, but there's some examples that I wanted to share with you. So the completeness of the budget. An important question is whether or not we're accounting for all of the important forms of nitrogen in the deposition budget. Are we really measuring a true total or modeling a true total for nitrogen? Well, we talked about the inorganic forms of nitrogen, but we know from measurements of precipitation that organic forms of nitrogen are also important. What I'm showing you here on the right-hand side is a map of the proportions of dissolved organic nitrogen and inorganic nitrogen in rainfall. And this is a data synthesis that Sarah Cornell put together in 2011. But what you can see is that if you look regionally around the globe, dissolved organic nitrogen is an important contributor to the total nitrogen in rainfall. If you take those data sets and look at them all together, on average globally, organic nitrogen contributes about a quarter of the total nitrogen in precipitation, with a similar amount measured in particulate matter. So we know organic nitrogen is important, but we don't measure it routinely in our North American networks. Even though we're measuring precipitation chemistry at more than 250 sites, we're not measuring organic nitrogen. And nor do our chemical transport models at the present time fully account for organic nitrogen. So our knowledge of organic nitrogen chemistry, sources, and fate is improving, but our models are not well developed yet in that sense. And so the basic take-home message here is that we know that our budgets are not complete. We're not fully capturing the organic fraction. And so the total deposition numbers are low by an unknown but likely significant amount. So in this case, a significant step forward would be to develop methods to measure bulk organic nitrogen and precipitation, and to be able to do that at all of our NTN sites. But the issue is that organic nitrogen is not very stable in environmental samples, and so we have to adapt methods both for the sampling and the analysis to accurately account for this organic nitrogen. So our networks need to evolve to include organic nitrogen. So moving on, and coming back to this idea of ammonia emissions in agricultural areas, an important question is whether or not our existing monitoring networks are properly capturing the spatial variability of ammonia in agricultural areas. We saw from the maps that ammonia dry deposition is very important in these areas. It makes a large contribution to the deposition budget. So what I'm showing you here is a map of the United States with county scale ammonia emissions. And the red areas indicate those counties where the emissions are very large. And then the stars are the locations of the National Atmospheric Deposition Program ammonia monitoring network sites. So there's about 100 of them around the country. But what you can see is that a lot of them are located in the eastern US where ammonia emissions are fairly low. There are large geographic areas in the agricultural regions like the Midwest where we're not monitoring in these high ammonia emission regions. So to give you a feel for some of the complexity of monitoring ammonia, again, I'm focusing on my home, or I'm picking on my hometown, which is okay. I'm exploding a view of Sampson County in eastern North Carolina. And what I'm showing you here, these yellow circles, are all of the locations for confined animal feeding operations. So these are pig farms, poultry farms, turkeys, chickens. And this gives you an idea of, first of all, how many there are, and the geographic distribution and the density. And then here's our one ammonia monitoring site. So this monitoring site is very important, but you get a feel for the potential for spatial variability of ammonia in this area. So this is important because we don't right now we don't use the ammonia monitoring data in the TDEP measurement model fusion procedure. This procedure, I talked about the concentrations that we measure at castnet sites: nitric acid, nitrate aerosol, ammonium aerosol. We take those measured air concentrations and we spatially interpolate them. And then we apply the modeled deposition velocities. Well, those are secondary reaction products, so they don't vary significantly spatially. Ammonia is very different. Can you imagine the spatial variability of ammonia in this region? So the fact that we don't have that spatial variability well characterized creates a problem for the spatial interpolation procedures that we use as part of the measurement model fusion. So at this present time, we don't use the AMON measurements as part of the procedure. We need more monitoring in agricultural areas to characterize that spatial variability so we can develop an appropriate method for using this monitoring data as part of the measurement model fusion procedure. So the good news is we have a lot of tools at our disposal to guide this expanded monitoring. For example, we could use satellite observations and our emission inventories to pick out those locations where we really need to be measuring ammonia. So if we were going to do that, we should also measure ammonium aerosol at those locations so we can get the total ammonia plus ammonium aerosol. So the message here is that we really need to expand our monitoring of ammonia in these agricultural regions to better characterize spatial variability. Okay, so spatial and temporal patterns in dry deposition. We talked earlier about the fact that the dry deposition component is modeled, and it's more uncertain than the wet deposition component. So we need measurements of dry deposition to quantify site-specific budgets, but more importantly, we need these measurements to improve the air surface exchange algorithms that are in CTMs, so to improve our dry deposition models for reactive nitrogen. The problem with the measurements is that, as I said earlier, these direct measurements of air surface exchange are expensive, they're labor intensive, so where they are conducted, they're conducted for relatively short periods of time. They're not conducted for a full year with enough temporal coverage to really develop an annual dry deposition budget. But they are conducted to investigate processes. So for a short period of time, several weeks or a few months, to look at the processes that are driving air surface exchange. And so the value of these data sets really is in improving the model algorithms that we use in chemical transport models. So what I wanted to show here today is give you a sense of the amount of data that's available, direct measurements of dry deposition. So these are studies that employ micrometeorological techniques to directly measure dry deposition or bidirectional exchange. And this is the number of published studies of these direct measurements in North America up until July 2019. So all the studies that we could find up to this point. And again, I've grouped these into oxidized nitrogen, reduced nitrogen, and then organic forms of nitrogen. And what you'll see is that historically, we have the largest number of studies have investigated nitric acid deposition. We have about 13 studies dating back to the mid-1980s or early 1980s that investigate dry deposition of nitric acid. So this is nice because nitric acid is an important contributor to the dry deposition component, and so it's been studied most extensively over time. We have 6 studies where oxidized nitrogen and total NOI have been measured directly, dry deposition, and then fewer studies for nitrate aerosol compounds like HONO and N2O5. For reduced nitrogen, studies that directly measure air surface exchange of ammonia, we have about 8 studies spanning back to the early 1990s, and then fewer studies for ammonium aerosol. But then look at the organic nitrogen compounds. We have a handful of studies that have examined air surface exchange of peroxynitrates, PAN compounds, and these are mostly in forest ecosystems. But then there's only a single study where the exchange rates of some of these other organic compounds have been measured directly. So these data sets are extremely valuable, and we're glad to have them because it's really helped with our model improvement. But the take-home message here is that we need more flux measurements. This is really a data and a knowledge gap. But we need 2 types of measurements. We need long-term sites for time-resolved, speciated measurements to investigate key processes in select ecosystems. So pick out some of the more important ecosystems and establish these long-term sites there where we're looking at processes and doing the best job that we can of speciating the total budget. But that's going to be very expensive. And by the way, we only really have one of those sites now, and it's Harvard Forest. Bill Munger's site at Harvard Forest is the only long-term flux measurement site in the United States. So we need more of those sites, but they're extremely expensive. So you can't put them everywhere. So we need these low-cost dry deposition measurements that we can deploy at a larger number of sites, hopefully within our existing monitoring infrastructure, where we may not be able to investigate processes, but we can at least investigate spatial and temporal patterns to develop dry deposition budgets. So the need for more dry deposition measurements is really a key data gap. So moving on, we talked a little bit about deposition in urban areas. So why do we need to know deposition in urban areas? Well, a couple of reasons. We need to know deposition to urban ecosystems. What are the impacts of deposition to urban ecosystems? We know that these environments are unique. We also need to know the contribution of deposition to water quality impairment downstream. Downstream of large cities, what is the contribution of urban deposition to water quality impairment? And we know that urban to rural gradient studies, so where we're looking at deposition from the urban area out to the rural area, our chemical transport models and satellites show these urban areas as hotspots for reactive nitrogen deposition. Here's another example from the TDEP measurement model fusion procedure, and this is a category, the mysterious other nitrogen category. So these are the compounds that we don't measure at the CASNet sites. I mentioned CASNet earlier. We don't measure all of the reactive nitrogen species at the CASNet sites, so we rely on the chemical transport model for dry deposition estimates for NO2, HONO, and some of the organic compounds. So that's what I'm showing you here is the contribution of the dry deposition of these other unmeasured nitrogen compounds to the total. So these red areas are where those other compounds are significant. And this reinforces some of the patterns I showed you earlier. These urban areas, so this is Atlanta, Georgia, this is Charlotte, North Carolina, and then on up the East Coast, these urban areas and these traffic corridors are hotspots for deposition of NO2 associated with mobile NOx emissions. So the take-home message here is that currently only 7% of the NADP NTN sites are classified as urban. So that network was not originally designed to assess deposition in urban environments, but we know that deposition in these environments is important. And so again, our monitoring networks need to evolve to better characterize urban nitrogen deposition. So now we're going to move on to an area where I spend a lot of my time as a researcher, and this is improving dry deposition models. And I want to give you a couple of examples here. And ammonia is something that I've spent a lot of time thinking about and working on. And ammonia is interesting compared to other compounds. If you look at nitric acid, some other compounds in the atmosphere, they deposit from the atmosphere to the surface. They're not emitted back to the atmosphere. But ammonia is different in that it's exchanged bidirectionally between the atmosphere and biosphere. So it can deposit, and then a few hours later, it can be emitted back to the atmosphere. So it's more complex in terms of the air-surface exchange processes. And as we saw, ammonia dry deposition is important to the total deposition budget, particularly in and downwind of agricultural areas. So this is ammonia air-surface exchange. Even though I've spent a lot of time working on it, there's a lot more work that we need to do there. So I wanted to talk to you about some of the details of ammonia air-surface exchange and some of the challenges. And so again, I'm showing you a typical forest in the US here. All the trees are the same. You have the net canopy scale ammonia flux, but that's driven by a number of different exchange pathways in the forest system. So an example is ammonia can be exchanged with the interior of the leaf. This is called the stomatal flux. ammonia can be exchanged with the waxy exterior of the leaf cuticle, particularly when it's wet. And ammonia can be exchanged with the litter, the leaves right on top of the soil, and the soil itself. And you'll notice that these arrows are going both directions, indicating that ammonia can deposit or can be emitted from that pool within the forest ecosystem. So those exchange processes combine to produce something called the canopy compensation point. If the concentration in the overlying atmosphere is larger than this compensation point, then the system will be a net sink for ammonia. If the opposite is true, if this compensation point is larger than the concentration of ammonia in the atmosphere, then the forest will emit ammonia to the atmosphere. So the challenge is to understand these exchange pathways well enough so that we can determine the canopy compensation point and the net exchange with the atmosphere. So I'll give you a little bit more detail, taking the leaf stomatal flux as an example. Inside the leaf, there's apoplast solution inside the stomatal cavity. So just like CO2 and water vapor, ammonia can pass through the stomatal opening. The apoplast inside the leaf contains some dissolved ammonia that's in equilibrium with ammonia in the gas phase in the stomatal cavity. So if that concentration of ammonia is greater than the concentration in the air above the leaf, then the leaf will emit ammonia. And if the opposite is true, then the leaf will take up ammonia. So this emission potential of the leaf is the ratio of the amount of ammonium in the apoplast to the hydrogen ion concentration. So when the pH is high and there's a lot of ammonium, that leaf has a high emission potential and will more likely emit ammonia to the atmosphere. But where it's very low, the leaf can take up ammonia. So we see that same process in the soil pore solution, in the moisture that's in the leaf litter, and in the moisture that's on the exterior of the leaves. And so there's a bidirectional exchange that's driven by this compensation point along all of those pathways. So it's the biogeochemistry that's driving the bidirectional nature of ammonia in these systems. So there are a number of research needs here, but one is that we need to improve our parameterizations of these emission potentials for leaves, litter, and soil. Our models are really built on measurements from European experiments. So we need more of these measurements in North American ecosystems so we can improve these parameterizations. We need to examine the role of surface wetness as a temporary reservoir for ammonia. So imagine at night the grass out there becomes wet with dew. Well, maybe not in this environment, but in North Carolina at night, a lot of dew forms on the surface. That dew can take up ammonia from the atmosphere. And then in the morning, when the surface dries, it releases that ammonia back to the atmosphere. So you can imagine this ammonia molecule is emitted from a feeding operation. It goes to a neighboring field where it's wet at night. The surface dries in the morning. It leaves there. It goes somewhere else. And so it's moving around different ecosystems. That's a real challenge for developing nitrogen deposition budgets. And then, of course, we need to characterize the leaf surface cuticle chemistry. And you can imagine how difficult that is to do. So these are some research needs for improving ammonia air surface exchange models. So in the last example, we talked about biogeochemistry driving the bidirectionality of ammonia air surface exchange. Well, some recent measurements of oxidized nitrogen fluxes in forest ecosystems are really challenging this unidirectional deposition framework that we use in chemical transport models. So these measurements of gas and particle air surface exchange are showing both emission and deposition of things like NO2, PAN compounds from forest systems. And so our models are assuming that all of these compounds are depositing from the atmosphere to the surface, where in reality, in some environments, they're actually being emitted from the forest to the atmosphere. So what I'm showing you here is an example of some work that was done in a ponderosa pine forest in California. This is some work from Ron Cohen's group, Min et al. 2014. There are a number of studies that have been done in this forest ecosystem. But what her results showed and what she summarized in this schematic here is that Their measurements of NO2 and nitric oxide showed emissions from the forest to the atmosphere. Their measurements also showed consumption of NOx within the airspace of the forest canopy and the production of peroxynitrates and alkyl nitrates, some of which were then lost from the forest to the atmosphere. So she observed, or they as a group observed, bidirectional exchange of oxidized nitrogen compounds in this forest ecosystem, which our models can't simulate. So whereas for ammonia, it was biogeochemistry driving bidirectionality, in this case, it's chemistry within the canopy airspace that's driving bidirectional exchange. So we need more studies that characterize the role of in-canopy chemistry and gas particle partitioning in determining the net exchange with the atmosphere. These experiments are obviously very expensive. We need to measure all of the compounds of the chemical suite of interest: ammonium nitrate aerosol, gas phase organic and inorganic oxidized nitrogen, and ammonia. So these are multidisciplinary, multi-agency experiments, very expensive. We need to further improve our parameterizations of the exchange with the cuticle in the ground, as I mentioned before. And if you think back to the slide where I summarized the measurements of dry deposition, there were none actually on the organic reduced nitrogen compounds, amines. We need to understand the importance of dry deposition of reduced organic nitrogen compounds, and we don't have very much information there at all at the present time. So those are two examples of areas where we need additional process level measurements to improve dry deposition models. So then moving on, this is one of the last topics I want to present to you, and this deals with subgrid variability of nitrogen deposition within chemical transport models. As I mentioned earlier, a lot of the critical load assessments for specific ecosystems use grid-based deposition output from models. But the spatial variability of the canopy physical characteristics, the biogeochemistry, the micrometeorology, create a lot of uncertainty in taking that grid average number and using it for a specific location. So let's say you're a resource manager in a forest in a 10 by 10 kilometer grid cell for a chemical transport model that contains some forests, some crops, a mix of land use. Well, there may be some large uncertainty in taking the model-derived value and downscaling it to your specific location. So for some locations, we see that as a large source of uncertainty. So I want to present to you a couple of examples here for nitric acid dry deposition and ammonia dry deposition. And in the top example, we're looking at nitric acid dry deposition to a deciduous forest. This is a land use specific estimate of dry deposition compared to the grid cell average. So a typical model has a grid size of 10 kilometers by 10 kilometers or much larger for global models, and this is the average deposition within that grid cell. And then comparing it to the land use specific flux to a forest within the same cell. Well, nitric acid is interesting because it deposits very rapidly. It's only limited by turbulent transfer. And so it deposits very rapidly, especially to very rough surfaces. And forests are obviously very rough. So this is an example that shows you that in some locations, if we look at Texas, for example, and in some forests here, where the landscape is very patchy, where within a model grid cell you have some forests and some other land use types, the dry deposition to the forest can be very different than the grid cell averaged flux. Some studies have shown factor of 3 difference in dry deposition rates. So that's a large source of uncertainty in downscaling numbers for specific ecosystem health assessments. Ammonia is even more complicated. This is an example showing the grid average flux versus fluxes specifically to croplands. And this model takes into account the bidirectional exchange of ammonia. So in this case, negative numbers of deposition indicate emission to the atmosphere. And what you can see is over these crop areas, Because the crops are fertilized, they contain a lot of nitrogen, they have a high ammonia emission potential, they're net emitters of ammonia to the atmosphere. But if you look at the grid average values for some of these same locations, you don't see those features of the flux. And so when it comes to developing nitrogen budgets for model grid cells, it's really important that we begin to use land use specific deposition estimates in our measurement model fusion techniques. These land use specific deposition approaches are emerging. We're using them now. One is the surface tile aerosol and gaseous exchange model that's been developed for the community multi-scale air quality model. But we haven't yet employed those techniques into our measurement model fusion procedures, and we need to make that advancement. Okay, so I'm gonna wrap things up now. We talked about a number of very specific knowledge and data gaps, things that we need to address to improve nitrogen deposition budgets. But there are several much broader research themes within those needs that span across the needs of a number of different stakeholder groups and present opportunities for enhanced coordination to move deposition science forward more rapidly. And when I say stakeholder groups, I'm talking about groups that use deposition data, resource managers, policy decision makers, scientists that need to evaluate a model or develop a deposition budget for a specific ecosystem. So those are the stakeholder groups that use deposition data. Improved understanding of the linkages between agricultural emissions and nitrogen deposition. That's a topic that you saw in a number of the different data and knowledge gaps. And it encompasses improvements in emission inventories, models, monitoring for spatial variability. Evolution of our monitoring networks to better characterize trends and patterns of deposition. That's a theme that came up over and over again, this idea that the networks that were developed in the 1980s to characterize changes in atmospheric chemistry associated with reduction in emissions of NOx and SO2 from power plants, those networks now need to evolve to better characterize agricultural sources and urban environments. And then finally, we didn't talk about this too much, but an overarching need is quantifying and reducing uncertainty in our deposition estimates for critical load applications. So reducing uncertainty in the total nitrogen deposition budget so that we can more confidently say whether or not the critical load is being exceeded. And so we need to improve our models, sure, but we also need to come up with methods for quantifying the uncertainty. Imagine how difficult it is to get an uncertainty number for the total deposition estimate from the measurement model fusion technique, which contains model output, measurements, spatial interpolation. So we need to develop those methods. And these areas are opportunities for federal agencies, academia, state and local agencies to collaborate even more than they are now. And there are some extensive and important collaborations that are ongoing through organizations like TDEP. But my message here is that there's always room for more collaboration to advance science more rapidly. So with that, I want to circle back to my acknowledgements. These are all of the people that contributed to the white paper and to our recent journal article in Science of the Total Environment. And so a number of people put time and effort into developing the material that I presented today, and I want to acknowledge them here. So there's my contact information. I'm happy to get more information to you if you're interested. And then my agency requires me to show you this. It's the disclaimer. You've all seen it. My agency is happy. Thank you very much.
Thanks, John. Very nice presentation.
Thank you.
Vamos a dar inicio a la sesión de preguntas, por favor, si gustan levantar su mano. Tenemos varias, no sé cómo empezar. Bueno, para los que no quieran hacerla oralmente, tienen el sistema menti.com 427934. I had a question for you, John. You talked about atmospheric deposition in the urban environments. Regarding reactive nitrogen, some authors talk about that we can increase the ammonia concentration in the atmosphere due to the bad use of the three-ways catalytic converters.
That's
what
right.
do you think about it?
That's a topic that I didn't talk about too much, but you're exactly right. Studies, not only in the United States, but in other areas, are showing concentrations of ammonia in urban environments that are higher than we would expect. And the idea is that there are important ammonia emissions from mobile sources. And so that's another aspect of urban deposition that we need to address in the United States. We know that the emission inventories are too low for ammonia because we're underestimating the amount that's coming from mobile sources. So you saw the network of ammonia samplers around the United States. Another thing that we need to do is expand monitoring of ammonia in urban areas. And another thing that I didn't mention is that we do have urban monitoring networks for air quality in the United States. We all know that. But we don't yet use those data sets for our measurement model fusion technique. So that's another improvement of the models for urban areas, is that we just need to use more of the available data in our measurement model fusion procedures.
Okay, thanks, John. Los invito a preguntar, pueden hacer sus preguntas en español. ¿No quieren levantar la mano? Choose a volunteer.
So I should select someone?
Anita, please. No? I have another question for you.
Okay, we have a brave person here.
Different authors talk about the nitrogen has the new carbon. What can you say about it?
It's an interesting concept. I mean, we're all familiar with the issue of carbon cycling, and I think that there's an analogy to nitrogen in that in a lot of places there's too much of it in the environment, but in a lot of places there's not enough nitrogen to develop food for growing populations. But I think there is a nitrogen issue. I believe in a lot of ways it's as complex or more complex in some cases than dealing with carbon, given the differences in sources, the complexity of how nitrogen pools change in the environment. So it's an interesting concept. I think the idea of thinking of nitrogen as the next carbon is exciting in terms of the broad thinking that will be needed to advance that concept.
John, please.
Do you think in the future we will be more carried about the nitrogen levels than the carbon levels?
That's a good question. I think the problems have a different scale. So I think it depends on where you are in terms of how much you care about nitrogen. In some cities and areas where nitrogen contributes a large portion of the particulate matter that you're breathing, you're probably more concerned about nitrogen than carbon in some cases. So I think it depends on where you are, the nature of the problem, but I think yes, in some cases, well, I think we are going to continue to care more and more about nitrogen. I think that's a fair statement.
For example, in the United States, that is more higher the concentrations of the nitrogen than the United States emits a lot of tons of carbon and nitrogen.
Yeah.
It's a big problem. I don't know in Mexico what is happening around the nitrogen, but
For us in the United States, the focus has really been on oxidized forms of nitrogen. And now it's interesting because the ecosystem health assessments have really raised the awareness of the importance of the reduced forms of nitrogen like ammonia. So it will be interesting to see in the United States if our regulations evolve to include reduced forms of nitrogen.
thank you.
Tenemos algunas preguntas del público que nos está siguiendo la conferencia desde afuera. Por favor, Carles, si eres tan amable.
Okay. More or less, the question is about the effects on the canopy of the forests, physiological effects because of the deposition of nitrogen on the canopy.
That's a good question. Nitrogen can affect the canopy through direct exposure to the leaves and through the systematic effects of the nitrogen in the soil that's affecting the diversity of vegetation species, the cycling of nitrogen in the system. So there are system-wide effects and there are indirect effects and there are direct effects. In the 1980s, when concentrations of sulfur dioxide and nitrogen dioxide were much higher, we saw more of the direct effects of toxicity on vegetation. And we don't see that as much anymore. The problems are more related to too much nitrogen deposition affecting the overall health of the ecosystem, and not so much the direct effects to the vegetation itself.
We have two more. The next is asking about the advantages of measuring nitrogen speciation in developing countries.
This is a very important question, and there's a technology issue here that needs to be addressed. We talked about the need for some very expensive measurements of air surface exchange and speciating the reactive nitrogen deposition budget. But I think in developing countries, we need to make available lower cost techniques. And of course we need this in the United States as well, but we need to advance the lower cost techniques that can be used, the passive sampling techniques, the low flow denuder techniques that are used in the United Kingdom and elsewhere. Lower cost techniques that can begin to be used in a large scale network type managed approach to speciate the important forms of nitrogen in developing countries. So I think it's important, but I think there's a technology issue and availability of low cost technology that needs to be addressed.
A third question is asking about the human activities with the highest effects in the position of nitrogen.
Human activities with the high, okay, that's a good question. Again, it depends on the location. As we saw in some examples, if you're in an environment that's near an urban area and the ecosystem that you're interested in is in an urban to rural gradient, the most important activities probably are mobile source emissions. Activities and emissions that take place in the urban environment that are related to oxidized forms of nitrogen. Again, we're learning more about urban sources of ammonia, but that would be an example where mobile sources are important. But if you're in an area that's downwind of an agricultural area, then it would be food production that is the most important human activity, and emissions of ammonia that are then depositing downwind.
¿Alguna otra pregunta? Muy bien. Como un mensaje, sobre todo para los estudiantes, nos percatamos que mientras más se avanza en la ciencia, aparentemente estamos investigando, pero encontramos todavía más dudas, o sea, muchos más parámetros por evaluar. En un futuro, varios de ustedes van a estar trabajando en algunos de los parámetros que todavía no medimos en México. Aún en Estados Unidos todavía hay un área de oportunidad, pero para eso estamos aquí, para que en algunos años ustedes estén divulgando toda esta información, no solo en nuestro país, sino en otras partes del mundo. Entonces recordemos siempre este panorama de las ciencias atmosféricas 2019. Muchas gracias a todos y thank you very much.
Thank you very much,
John.
Thank you.